Thank you. It is our pleasure to be here with you today. My name, as Alessandra mentioned, I'm Amr Hilal. I'm an assistant professor in the University Library. I'm head of the informatics lab. And my colleague here, Chreston. He is the data informatics consultant in the Data Services University Library. And most of our work is in, we support and collaborate in research with the research community here in Virginia Tech and beyond. And most of our work currently lies in machine learning. That sounds great. So based on this, let's go ahead and get started. These are our objectives today. We're gonna try, so first of all, the course that we usually teach is called Demystifying Machine Learning, which is like the code name of our introduction to machine learning. We just to make it like cool, so demystifying. So the objectives of our course is to identify when computer program is a machine learning program and when it is needed. Because the fact of the matter, folks, machine learning is like a buzzword, and people like, oh wow, let's use machine learning. But sometimes using the traditional methods can be better than machine learning. So you need to be clear and know when you need to use machine learning versus when you need, it's better for you to stick to the traditional methods. We are going to look at the difference between machine learning and other buzzwords like data mining, data science, deep learning, artificial intelligence, and so on and so forth. And then we are going to see the major types of machine learning. Those are the supervised, unsupervised, and other stuff. And then we're going to see the major components. How would you establish a machine learning pipeline or machine learning system? And then we're going to end with some cool stuff, seeing some example applications of machine learning in different disciplines. So this is our agenda that I just mentioned. So without further ado, so it turns out, folks, that we use machine learning in many things in our life. Maybe even we don't know that they use machine learning. Like, for example, simply when you type your search in the search engine you use, and a side note here, there are other search engines other than Google. For example, the recommended words, keyword search, like here, as you can see, the example, how Google or in the search engine, how does it come up with these words? That's a matter of machine learning. It depends on the information that the search engine knows about you. It depends on where are you, and so on and so forth. And so it actually looks at all this information and find the best suggestions for you to be the keyword as you start typing. Now, on the other hand, when you type your search query, the results of this are also a matter of machine learning. Which one goes first? Like even the ads that you see on the side of the search results, this are also listed or put based on machine learning. If you guys are following that tension that arose before, it's actually causing a lot of tension between Facebook or Meta and Apple. When Apple started to limit the application's ability to collect your information from your phone. And that actually impacted the business model of Facebook. And why is that? Because they rely heavily on the information they know from you or about you to find you the best ads that suit you. Because if they actually show you ads that are not tuned to you, then you are less likely to click, which means you are less likely to convert into money or to profit for them. And actually, Meta have just announced their quarter reports, and it seems that they actually said it clearly and openly that their profits have been impacted heavily by that practice. Maybe they said like billions of dollars they have lost because of this. And interestingly enough, very recently, Google announced that it is going to follow this model, but it seems that there was some kind of coordination between Google and Facebook about this. So I don't want to go into a tangent, but this is how much this information are important for those machine learning models to work. Because at the end of the day, the machine learning model, which works or learns from two sources, the data and the assumptions that you inject into it. But we'll get to this later. Now, another example is the spam filter in your email box. How does it actually classify that an email is a spam? So you can think that it looks at the words inside, how the words are spelled, how the words are written. You probably can recognize that usually spam emails have like capitalized words that usually have like a lot of money, like and so on and so forth, when, come, and stuff like this. So it actually, the spam filter or the machine learning model behind the spam filter, it looks for all these signals, and not only signals that exist into the text of the email, but also other signals that exist in the email header, if you have heard about this before. So that's kind of network headers that actually exist with the email. You can actually view your email header from your mailbox. For example, where the email comes from, the IP that the email comes from, the service, the server that it comes from, and so on and so forth. So those are also signals that the spam filter tries to use to classify an email as a spam. But even with that, sometimes the spammers who are always in a continuous battle with the model in order to beat it, they can actually cross it. That's why from time to time, you find a spam email that comes into your inbox, which means that the spammer actually could cross that filter. And that is, I mean, when that happens, the model of the email service asks you to classify this as a spam. Why? Because the model is going to learn from your signal. In future, it will actually try to figure out or capture this as a spam in the future. Another nice example of application is the image processing and video processing. As you can see in this picture, that you can see similar applications on the social media. For example, capturing the faces. You can find this in Facebook, Snapchat, stuff like this. It can actually capture that this is the face. It can actually tell you that is this person John? Is this like Hannah? And so on and so forth. Like, let me just give you like a simple example here. In Zoom, you see those filters. You see the glasses on my eyes now. So the question here is, how does the model, how does the Zoom knows that those are my eyes? Like, see, if I move my head now, actually the glasses moves with my head. So how do they know that those are my eyes, and it actually keeps tracking me? That is actually machine learning as well. So a lot of applications. But the question now is, I mean, how machine learning and why machine learning, and how long have been people trying to get the machines to learn? So it turns out that for a long time, people wanted to build intelligent machines. Those are who can mimic the human intelligence or human smartness. But it turns out that very few problems can actually be simply programmed. And what do you mean by programmed? Like the typical programming, I believe that all of you have even like a slight or small experience with programming. When you do programming, you actually try to decompose a problem into simple rules or steps, and then code those steps into a language that the computer understands, and then write it and give it to the program, to the computer to execute. So as I said, it turns out that relatively few problems can actually be done like this. For example, as you can see this example here, if you have a graph like this, how can you know the shortest path between node A and node F? This is a very common problem in computer science, and we know an algorithm that have specific steps and rules to do this, and we can actually program the computer to do it. Another example is the calculator. There are definitely certain steps and rules to do addition, subtraction, multiplications, and division, and many other types of mathematical equations or arithmetic equations. And those are actually programmed into the calculator. But other problems that are very interesting that do not fall within this. Like, for example, for problems that you cannot even describe. Let's say, for example, here in this picture, if I tell you how would a mug look like, so you can actually tell me, yeah, it might look like a cylinder and it has a handle, so on and so forth. But how would you describe this to the, excuse me, how would you describe this to the computer? Because mugs actually can take different shapes. If we make it even more complex, if you're trying to make facial recognition, how would you describe to the computer what a face looks like? How would you describe to the computer how would the eyebrows look like? I mean, think about it in your head. It's almost very, it's very hard to recognize this or to describe it to the computer. And so we cannot actually follow the same programming model that we have just described. Another example is the translation, machine translation here. Like even though there are language rules for translation, but there are always so many exceptions. There have already been trials to do machine translation before machine learning, but they were not as successful as we have now. So it turns out that the only way to solve those very complex problems, which are at the same time very interesting problems, and we look for them, is to let the machine learn just like we as humans learn. Because you and me can recognize the faces. Like probably you have been seeing me now for 5 or 10 minutes. Now, if you see me, if I put my face within like 10 other faces, now I believe you can recognize me. Now, can you know how my mind works with that? The fact is, it's very hard. So that's why I said, it turns out that the only solution is to let the computers learn just like we learn. All right, so now, based on what we have described just now, the difference between machine learning and traditional programming. So folks, you can now hear the siren here. It's a test. So I mean, do not panic. We're good. We're fine. It's just a test. I didn't know that there is a test now, to be honest. Excuse me. So based on what we have just described, the difference between machine learning and traditional programming is as follows. In traditional programming, you write the steps of your problem and feed it along with the data to the computer, and the computer produces an output. Again, you write your program, feed it to the computer, and then give it an input data, and the computer will produce an output. Like, for example, the shortest path or the calculator. Now, in machine learning, we do something different. We feed the computer with data and outputs, all right? Just like you and me, we learn from our experience. And experience is something that you go through, you receive some inputs from the environment, and you actually interact with this experience and produce a result of this experience. And from that, you learn how you react in future. So similarly here, for machine learning, we feed the computer with data and outputs and a way for it to learn. So back to machine learning. So we feed the computer with data and output, which represent an experience, and show the computer how it learns, and the computer will produce a program. Now you use this program in future to make future predictions, all right? So in other words, the computer now will convert the experience into expertise. All right, I forgot to say at the beginning, if you have any questions, please raise your hand or type your question in the chat, and I will try to respond to them as I can see them. So how does machine learning came to exist? So actually the term was coined by Arthur Samuel in 1959, excuse me, who developed a checkers game when he was at IBM. Arthur Samuel actually came to fame when he actually graduated from MIT in 1926 and joined Bell Labs in 1928, and then he joined IBM in 1949. And he came to fame when he actually developed his checkers game. So Arthur Samuel thought that why we do not let the computer come up with its own rules instead of us telling it its own the rules. That's what I have mentioned, the difference between programming and machine learning. And he actually thought, why I should not develop a checkers game and let the computer actually get this experience. What was interesting though is that Arthur Samuel was not a good checkers player. So what he did is actually he had to program a lot, or actually tens of thousands of games with his computer to teach it what are the good and bad moves. So he wanted to the computer, as the computer interact with him, that he knows from the experience what are the good and bad moves. And he actually managed to produce the first machine learning program that does this. And of course, you can expect that took him a lot of time, which is something if a human would do, would actually take them like a longer time, much longer time. But the computer actually do not suffer from the patience problem that we have. Probably the computer would suffer from computation problem, memory problem, which was actually something that was limiting at the time that he was developing his checkers game. So in summary, AlphaSam will manage to get the computer to learn the checkers game by converting the experience into an expertise to be able to play checkers game. So at a high level, machine learning applications learn from experience like human learn without direct programming. And we have explained what is programming. Machine learning is the ability to adapt to new data independently through iterations. So notice that there is an important difference that distinguishes machine learning application from direct programming. That is, machine learning applications can adapt, can actually consume new data points and learn from them and keep adapting to this. And it does actually this excuse me, through iterations. Machine learning basically is about pattern recognition. In other words, it sees like a bunch of data, a bunch of experiences, and it starts to build or chunk some kind of understanding of this problem through pattern recognition. And it actually uses probability. It's not solely based on probabilities and statistics, but it actually uses probability to produce the best results. As formal definitions, Arthur Samuel in 1959 had this definition for machine learning. It is the field of study that gives computers the ability to learn without being explicitly programmed. And Tom Mitchell from Carnegie Mellon in 1998 have a more modern definition. So he said that a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P, if its performance at task in T as measured by P improves with experience E. So if we apply this complex definition to the checkers game, the experience E was playing many games of checkers, and the task was winning the game. And the P, which is the performance, is the probability the program will win the game. So it is trying to improve that probability as it learns. Now let's get to some interesting stuff. So what actually the drivers of machine learning? So the first thing is the internet. Since the advent of the internet at the late 80s and early 90s, and as we move on through the time, the internet created tons of data. I mean, even now, people started to speculate with the advent of Internet of Things, if you have heard about this term before, when you have your car has computers, your washer has computers, little computers, your refrigerator has computers, and everything, you have computers everywhere, and those are generating data. And that actually torrent of data that we can see now started to be even more than the capacity of storing those data, to the point that we actually, there are some reports that says that the capacity that on Earth that we have to store the data is actually less what we produce. And therefore, there might be some data now that we cannot, we just have to use them on the fly or just throw them. We can't store them anymore. I mean, those are the data that are generated, for example, from edge nodes like your car, your, as I said, your refrigerator and stuff like this. Another driver for machine learning is the computation power, which actually gave the rise to neural networks in the 2000s, early 2000s. And just to give you a little bit of glimpse of that, you just know that the data centers right now, and this the life we live in, maybe this number is actually a few years old, they consume more than 2% of the global energy consumption. You consume a lot of energy in the processing and also in cooling the computers that work on those data centers. And with more computational power, we'll be able to solve more complex problems that require a lot of processing. Another driver is the existence of harder problems. For example, the problems that require processing large or huge amounts of data. For example, the electronic medical records or biology and genes and stuff like this. Those are problems that require processing a lot of data, which may not actually suit very well to directly program them because of so much data and maybe also so many exceptional cases. And as we said before, applications that cannot be programmed by hand, for example, handwriting recognition, like the post office that actually captures the address and all the information that you write on your letter in the envelope. This is usually captured by machine learning models. that are trained on so many styles of handwriting. So it's not only tuned to use, it's for everyone. Natural language processing and natural language understanding. And we're going to see a nice example on that at the end. Like this video here shows you, for example, an experiment that was done in Stanford, I guess. So this plane that you're going to see now was actually trained to fly using machine learning. Because how would you fly at an airplane is not something very straightforward. You and me as people, we can do this, but there's so many exceptional cases that they actually, when they apply machine learning to it, it turns out to be like a much better experience. And this is actually what they try to do now with even the self-driving car. So let's see this video. So as you can see, the plane is going to learn when it does a mistake, how it is actually trained to flip, to always go to the right position based on the signals on that it actually reads from its surroundings. I mean, for example, the height, the angle, and stuff like this. So this plane was actually trained using machine learning. Another type of harder problems are the self-customizing programs, like recommender systems. Like one of those recommender systems, for example, in Netflix or in YouTube, how does the Netflix or YouTube shows you the next video that they think that you should watch? That's a recommender system. And notice that this is not only customized to you, it's the same problem, same application, same model that works for everyone. So it actually works based on what you have watched before, who you are, what do you buy, what do you do, based on all the information that they know about you. They think that this video might be the best video for you. All right, just to give you how much the data that we have now, as you can see here, by 2025, we expected to have the annual production of data to be 175 zettabytes, and 1 zettabyte is 1,000 to the power of 7, so which is 1 with 21 zeros. Okay, so it's 1,000 to the power of 7 beta. So that's a huge number. So let's now see some differences between machine learning and some other buzzwords. So the first word that we are going to talk about is data mining. You probably have heard about this word before. So data mining is also known as the knowledge discovery in databases, or KDD. And just to be clear here, the borders between machine learning and data mining are sometimes blurry. So, I mean, you might find some kind of different definitions, but I mean, they all go around some basic differences. So basically, as we said, there are overlapping methods between machine learning and data mining, but they have different goals. For data mining, notice, I mean, focus with me here, folks. So data mining is all about knowledge discovery of previously unknown properties. So for example, let's say that you have a bunch of data, and you would like to find insights inside this data. Let's say, for example, you have data about the shopping habits or shopping activities of, excuse me, of people, right? And you would like to introduce a new product, and you would like to see whom should you introduce to, I mean, how would you introduce it, when, and so on and so forth. So you can use the data you have about the shopping activities of people and try to find some insights that can help you with that. So this is called data mining. So again, knowledge discovery of previously unknown properties. Now, machine learning is about prediction based on known properties. So you already know some nice, insightful properties of your data, and you would like to make a prediction based on those. And the fact of the matter is, we actually sometimes use data mining and machine learning as a pipeline. So you use data mining to extract some interesting features about your data, and then use those interesting features to feed into a machine learning model to do prediction. So data mining produces information, while machine learning produces an algorithm. Remember when we said the difference between programming and machine learning is that machine learning produces an algorithm, a program. Data mining also can be manual. There are some techniques that can be manual, while machine learning is always automated. And examples are anomaly detection, finding what could be an anomaly in a system, and also cluster analysis, which is if you have a bunch of data and you would like to put them into like 3 buckets, how would they look like? So those are actually some examples that actually fall within the intersection between data mining and machine learning. So data mining and artificial intelligence. So artificial intelligence, again, is one of those terms that you will have a lot of definitions, and you might, there is no like a clear-cut definition for artificial intelligence. But I mean, what I'm going to tell you now is one of those definitions. But I mean, if you come across some other ways of defining what is artificial intelligence, so I mean, it's okay. I mean, as I said, it's kind of like a very broad term. So it turns out that theoretically, people have always thought that any kind of machine that they manage to build that mimics human smartness is an artificial intelligence. So a calculator or a computer at the time it appeared was a type of artificial intelligence because it was actually mimicking a human intelligence. But practically speaking, we always refer to those applications at the very top notch of artificial human intelligence, mimicking human intelligence as artificial intelligence. So when we talk about machine learning, deep learning, those are what people now call or refer to as artificial intelligence. No one now calls calculator or a computer as an artificial intelligence application. So machine learning is at the leading edge applications of artificial intelligence. That's why we usually use if you probably have seen this AIML. I mean, artificial intelligence usually coined with machine learning because machine learning is actually a sort of artificial intelligence. Deep learning, also known as deep neural networks, is actually a specific type of machine learning applications that includes a big structure of small traditional units of machine learning that we are going to see in a few slides. It is actually capable of processing more or harder problems, very complex problems. And as you can see from the name, it actually tries to mimic how our neurons in our brains work, even though it doesn't exactly work like the human brain neurons, because we actually don't know so far how they actually exactly work, but we're trying just to see how or mimic this. Examples are face detection, natural language processing, and understanding. Those are very hard problems that neural networks actually excel in processing them. There are different network structures in deep learning, since we said that they are connected units. So you can expect to find several different architectures, and every structure can work with specific types. Actually, and so many structures can work with every type of applications. But I mean, as people try and different architectures, they figure out that those are some of the nice architectures that work for this particular problem, for example. And deep learning is also at the leading edge of applications of artificial intelligence. So just to put those 3 terms together. So as you can see here, artificial intelligence is, the broader umbrella of all those applications, and it started like very early. Machine learning is at the machine learning applications when it started to pick up. That was a subset of artificial intelligence applications. And then deep learning is a subset of machine learning applications. And as you can see, all of them are currently, at the edge of what we are doing now. Actually, Chreston and myself just came back from a conference, machine learning and deep learning conference in San Francisco. And it's very interesting to see every year, how far and how advanced the applications of machine learning and deep learning have reached. So machine learning versus data science. I believe that all of you have heard the word data science. Data scientist is one of the highly lucrative jobs now, very demanded job now. So data science is an interdisciplinary field that uses different scientific methods, algorithms, and systems to extract knowledge from many structures and structured and unstructured data. As you can see from the figure, data science is at the intersection between the figure that we have seen in the previous slide, deep learning, machine learning, artificial intelligence. It actually uses those tools to do some processing, and actually also uses some other tools from the math, statistics, visualization, exploratory data analysis, and so on and so forth. So in a nutshell, you can think of data science as a whole methodology, a whole system, a complete process, versus machine learning is just a tool or a step within this process. Data science uses, as I said, machine learning, artificial intelligence tools, but it is not part of it. And finally, machine learning versus other scientific fields. So machine learning is actually built on top of different components or different components from different disciplines. That includes linear algebra, calculus, probability and statistics, computer science, and so on and so forth. So because this is important to know, because some people think that machine learning is purely statistics. Yes, machine learning uses a lot of statistics, but yet there is many other tools from different disciplines are used. For example, we use optimization techniques to solve some problems that we have derived those problems using statistics, but we could not find a direct solution for them. So we actually use optimization techniques to find the optimal solution for those techniques. So based on all what we have said, when do we need to use machine learning? Number one, when your tasks are too complex. Those can be tasks that can be performed by animals or humans. There are no well-defined program for it. Remember what we have said at the beginning, so driving, speech recognition, image understanding, facial recognition, and so on and so forth. And tasks that are beyond human capabilities, like turning medical archives into medical knowledge, weather prediction. For all those types of problems, folks, you can expect that even though there are so many factors that contribute to this, and those factors, you might find some mathematical models, real models that are not built on machine learning, that can deal with them, but you cannot find a particular model or one system that can actually deal with all these factors together. I'll give you an example. My PhD was in computer networks. I was dealing with wireless networks and the interactions between humans, people, and the network. And I needed actually to build a system to study some phenomena that's based on how people move within indoor environments. So the fact of the matter is, I have some mathematical models that model how people move within a system. And I have some models for shadowing and some effects of how the people actually impact the signals from, let's say, your Wi-Fi signals. But I don't have one closed formula, closed solution for all these factors together. So in order to solve this problem, I had to run a simulation. So the simulation is just like islands of different models that do not have one certain model that brings them together. So we put them into the simulation and let the simulation actually connect them together by following some kind of realistic scenario of them working together. So the same thing here, for weather prediction, all these kind of things, you might or you may not find some small models for parts of the problem, but you may not find all of them coming together or working together using only one model. And for those, there might be a solution to work using machine learning. And back to the question that I mentioned at the very beginning. If you have a model that can physically imitate or actually study a certain phenomenon, let's say, for example, Newton laws. For the simple examples, you don't have to use machine learning to solve those equations. Because you have like a deterministic solution for those. Now, at the end of the day, machine learning is going to give you kind of a probabilistic solution. If you remember, we said a few slides ago that machine learning at the end of the day is going to produce you the prediction that relies on the highest probable solution. So if you have a solution that solves your problem very deterministically, then probably that's better than machine learning. On the other hand, some of those deterministic solutions can take very long time to work. So in this case, you might think, okay, maybe if I use machine learning, it will make my life easier. It can take smaller time. So think about those factors when you think about using machine learning. Another point to this is, as we're going to see later, there are different levels of complexity of machine learning models. Always try to think about the simplest model of them that can work with your task or your problem. I mean, if your problem can be solved with a simple solution, then don't try to go directly with the more complex. Start with the simple thing first, if you know that this is going to work. All right, the other type of machine learning, other reason why when we need to use machine learning is we need adaptivity. As we said before, traditional programming, when we use traditional programming, once the program has been written and installed, it will stay unchanged, just like the calculator. While in other programs of machine learning, it can adapt to systems. I mean, as you get new data, can actually adapt to them. So you can actually train your model with some experience. And when you get a new data point that you have not seen before, but it looks similar to what you have learned before, you can actually deal with it. It can give you like a good solution or a good prediction. Example for that also is recommender systems. Many other examples exist, but the recommender systems is what I have described, like what you see in YouTube and Netflix. All right, so before I get to the major types of machine learning, let's see if you guys have any questions so far. So please raise your hand, type your question, or maybe unmute yourself and ask. Any questions so far?
I have a question. Is it possible to learn or to understand what the computer you put in machine learning, you put in the output and the data? And is it possible to understand how the computer processes the data and comes to the program?
That's a wonderful question. Thank you so much. Actually, that's one of the major problems right now with artificial intelligence and machine learning. The idea here is that one of the major advantages of programming is that you know what you type, right? You know the steps, and that's what actually makes your problem even traceable. When you have a problem, you can go back and know where this is coming from. But the problem is that we figured out that there is a trade-off between understanding and data. So the more you understand about your problem, the more you can explain your problem, okay, the less data you need. So for example, when you talk about Newton's laws, you know why this is happening, right? We understand, we can explain the phenomenon, right? That's why we don't need a lot of data. I mean, we can just, we can deduce the laws and write the laws. Now, for facial recognition, you don't know why I can recognize this as an eyebrow. You don't know why I can recognize this as a nose. That's why we need a lot of data to make up for that. And that actually makes the lack of explainability here, the lack of interpretability, the lack of understanding of the problem, makes this of the problem that I try to solve, makes this problem that we don't actually, in many cases, as our model starts to become very complex, we don't understand why it works and how it works. We just know that the model works from the measurements that we have, the accuracy, for example. Okay, but it turns out that we don't know exactly why it works. And this is what they call artificial intelligence explainability. I mean, they call it XAI. So they actually now working on explainable AI, and sometimes they call also interpretable AI, which is the difference between explainable AI and interpretable AI. So explainable AI is the fact they try to know, like, design the system so that they can actually know after. I mean, when we do the experiment and we see the output, we can know why this happened. The interpretation is that it was that the system was designed with some kind of intervention inside to actually make it, as it moves forward, more interpretable. But so back to answer your question. So far, this is a major problem in machine learning. Sometimes, yes, I mean, we cannot know for sure why it actually produces this. In one of the conferences that I attended, they actually came across this nice example. One of the researchers, he actually he was working with the Siri, you know, the Siri, the application in iPhones. He actually noticed that many people, when they try to test, they actually test like very tough examples. He actually tried to test Siri with very simple and naive examples, and turned out that it does not solve them very well. And there is a lot of faults, right? But the problem again is, I mean, those are not explainable models. So we don't know actually why this can actually, why these problems are happening. The problem here is that the debugging is very hard. And since we have talked about this, one of the other problems in artificial intelligence in general is their generalization. So it turns out that when we train a model on a particular example, let's say train a model to play cards, okay? As you train it a lot, I mean, you can expect to have a model that is, I mean, excellent in playing cards. Now, you can easily find people who can play cards and chess at the same time. I mean, they are capable of doing both. But it turns out that in machine learning, when you train a model to play cards, and then want to train the same model, we would like to, again, simulate a human being, a human brain. When you train that model to play chess, we get into a problem called catastrophic forgetting, which is the model will learn to play chess, but it will forget to play how to play cards. So that's another problem that they are dealing now with artificial intelligence, which is to make the problem of the model general.
Virginia Tech has deactivated the previous alert.
Sorry about that. So they call this actually artificial general intelligence, AGI, right? So I'm not sure, did I answer your question? So the answer to your question is, this is an active problem in research. Yes, the models, because we actually, by nature, by definition, we use machine learning because we do not understand the problem. Actually, the model is not very understandable, it's not very explainable. So we don't know actually why it produces those outputs. Does that answer your question?
Yes, it does, but then I come up with the next question, if I may. Because if I want to use it as a scientist, this means for me that I should use machine learning only in those types where I'm not interested in the model itself, right? But only the output.
Probably yes. Well, I mean, you will have some idea about the basic theory of what you are working on, but sometimes there are very many factors that contribute to your problem, and you don't have even a model, even in theory, that brings those factors together. So you just use machine learning to find out how, like, let's say, like a predictor, some kind of an independent variable that you, or dependent variable that you depend on those factors. So yes, I mean, mostly you will not have a certain model that actually can explain how those factors come together to study your phenomenon or to explain your phenomenon. But probably subsets of those, how they work together. So I mean, yeah, that's the answer for your question. I mean, probably you will not have that background.
Thanks.
You're welcome. All right, so it is 9:53 on my clock here. So let's take a 5 minutes break, and we will be back here at 9:58. Sounds good?
Thank you so much.
So,
all right. So so far we have seen what is machine learning, what is the difference between machine learning and some other buzzwords that we hear around. So we'll start to see a little bit what are the major types of machine learning. We are not going to get into technical details here. That's actually one of the major core things in this courses, or this short courses, not to get into the technicalities so much. So without further ado, so the first type of machine learning is what we call supervised learning. So as we said, if you remember the one of the very early slides here, when we differentiated between typical programming and machine learning, we said that in machine learning, we feed the computer with data and output and produce a model or a program. Actually, there are two types. In one of them, we feed the model with the data, which is the independent variables, the predictors, if you would like to say, they have different names. And also with the output, which we call the label. All right, so it's input and output, and which is the typical thing that we have talked about so far, and let the model actually try to predict in future the output of the label based on incoming data. And there are two types of this. The first one is regression, as you see at the top example, for which the output is a continuous value, right? So examples for that is, for example, housing prices. Let's say that you would like to predict the price of houses based on some features of those houses. For example, the number of bedrooms, number of bathrooms, the school district, the age of the house, and so on and so forth. So you can use all these factors and try to predict the price. And the price is typically a continuous scale value. Another example, interesting example, is to try to predict the age of a person given their picture. Okay, so the input here is the pictures, which is typically going to be the pixels of the picture. And then you would like to guess the age, and the age also is a continuous value. Now, the other type or the other category of supervised learning is what we call classification problems. The difference is just that the output is a discrete, An example for that, if you would like to use machine learning to use, for example, X-rays and medical records, all sorts of medical records of a patient, and guess if the tumor that they have is malignant or benign. Okay, so being malignant or benign is actually a discrete value. It's either 1 or 0, malignant or benign. In some cases, we can actually have more than one.
Sorry, Amr, the sound is broken.
All right. Has it been broken for long? Is it good now?
It was good before for me.
Can you hear me?
Yes.
I can hear you just fine.
I think it's good.
Me too.
Same here.
Okay. All right. So again, the regression problem or the regression category is when you have a continuous value output versus classification when you have a discrete output. As we said, the difference when you try to classify a tumor, whether it is malignant or benign. And this is a binary classification problem, but the fact of the matter is there are so many classification problems that will have multi-class. Let's say, for example, if you would like to guess, given some information about two teams, the result of the game, whether it's win, lose, or tie. That's 3 cases. In some other cases, for example, you can have, let's say, like one of the problems that Chreston and I are working on is to use images of crop fields captured by drones and try to guess the wilting scale of within those plots that the drone will capture the images of. And the scale is from 1 to 5. So we have here 5 cases. And you can actually have much more than this. So, I mean, it depends on the nature of your problem. So those are what we call the supervised learning problems. You will have to have the data and label output and the label. And by the way, in the early days of machine learning, and even until today, some problems you will suffer from the lack of labels. I remember early in the days when I was doing my PhD, my friends who was like contemporary to me, they would always send you like a link. I mean, could you please label those pictures to me? Let's say that they were trying to train a model to find cats and dogs. So you will need to have some pictures along with the label, whether this is a cat or a dog. All right, so this is the label that we're looking for. And until now, as we're going to see in a few slides, this is still a major problem in many of the cases that you have the data, but you don't have the labels. The other major type of machine learning is what we call unsupervised learning. In unsupervised learning, we feed the model only with the data and there is no labels, which is, if you guys remember, that's one of the areas that is very overlapped with data mining. Because now here, we would like to find interesting patterns or interesting features within this data, which is knowledge discovery, as we have probably alluded to when we talked about data mining. So for example, if you have some data and you would like to put them into different clusters, as we said, the example of the customers, and you would like to put them into different customers so that you can apply different business models to them, pricing models and stuff like this. dimensionality reduction, which is a type of problem that you can use to reduce a very highly dimensional set of data into small dimensional data. And when we say dimension, this means a feature. So if you have a problem that can be described in 10 features, those are 10 dimensions. Okay, if you do so, when you look at x1 and x2 here, each one of those is called a dimension, which is a feature, in fact. So this is the second major type of machine learning. The third major type of machine learning, which is even though it's kind of less existing. I mean, you don't find it so many now, but it's actually continue to pick up. It's called reinforcement learning. In reinforcement learning, you use a system. The model learns from an interaction with a system, which is a major difference between reinforcement learning, or RL, and the other types, which is in supervised or unsupervised. In supervised and unsupervised, you have a set of data ready for you in the vast majority of the cases for the model to learn from. Okay, but for reinforcement learning, we don't have the data ready. We have to get the model interact with the environment, and based on what those interactions, it can actually uses a kind of reward function to decide whether this was a good move or a bad move towards a goal. Like, for example, here, if you see this robot that is trying to reach this jewel. So if it goes into this direction, mostly this is right. I mean, this is a good move. Okay, it is not right or wrong. It is a good move. If it moves to this direction, to this tile, to the top tile, this is going to be less rewarding, because yes, I mean, it's not, it will not help the robot to reach the jewel, but the robot can go back, right? If it goes to here, it will get more reward. If it goes to here, it will get more reward. If it goes up, now that's not a good reward. I mean, you will get less reward. So the goal of the model here is to train the robot as it deals with the surroundings to figure out what could be a good move, which is another major difference between reinforcement learning and supervised or supervised learning, which is in supervised learning, you know for each data whether this was right or wrong. If you see a picture of a dog and classify it as a cat, you know this is a wrong result. Now, in reinforcement learning, we don't use wrong or right. We just use reward and penalty. Okay. So the model at the end of the day learns by maximizing its reward and minimizing its penalty, and it's basically used in games and real-time decisions, and actually used a lot even in political science, and because it actually requires it deals with system with consequences or sequences of decisions that actually affect each other. So when you make a decision, that will actually impact your decision in the future. I mean, which is basically the nature, for example, in politics. So to putting those three together, I mean, I will leave you with this. With this figure to look at, with some the major three cases of machine learning and with their typical applications. But there is actually hybrid types of those three, and they are basically motivated by the lack of enough labeled data. As I said, I mean, finding labeled data is one of the major problems in machine learning. The first type is called the semi-supervised learning, and it actually combines, trains the model with a small set of labeled data and a large amount of unlabeled data. All right, I mean, the details of this is beyond the scope of this lecture, but this is how they work. It turns out, I mean, we don't have enough labeled data, so let's use both. All right, another technique is called weak supervised learning, in which you probably, I mean, don't have a small set of data, but you have a source of noisy labeled data, okay, or imprecise source of labels. So you use it to provide like a signal for labeling the large amounts of data, which is at the end of the day, it's better than having no label. So it's just other ways of putting things together to overcome the problem of labeling the data.